Okay, so for today's lecture, we're going to look at the synthesis of multi-substituted aromatics. And last time I'd given you a list of a couple different compounds to propose syntheses for. So we're going to start with meta-dichlorobenzene. The first thing we want to do is convert the structure into a name, or the name into a structure, with meta being the 1,3 relationship of the two substituents, which are both fluorine. So we have 1,3-dichlorobenzene. And so basically, before we get into the actual strategy, we can say, how do we get fluorine onto a ring? So we can do a little retrosynthesis here, and we can say that fluorine is installed through the diazonium substituent. The diazonium in turn comes from the amino substituent. The amino substituent in turn comes from the nitro substituent. And so we know how to get nitro onto the ring, and so that's what we're going to start with. So our retrosynthesis arrow here, there's no carbons bonded to the ring itself, so we're just starting with plain old benzene. So the first thing we want to do is get a nitro group onto the ring. So we're going to use nitric acid, sulfuric acid to take benzene to nitrobenzene. So now we have nitrobenzene. The nitro group is a deactivating group, and it directs to the meta position. So with the red marker, I'm showing where it directs, and the red means that the ring is less reactive than benzene, so the next reaction takes place slower than the reaction of benzene itself. So notice this is exactly what we want, 1,3, which we need to achieve to get the desired relationship. So we're going to do a second nitration. Again, you could actually almost do this in one pot if you control the equivalence of nitric acid that you use, but we're going to show it stepwise. So now we have 1,3-dinitrobenzene. So according to our scheme here, we have both nitro groups on. Now we need to reduce them. So the conditions we can use for that, there are a couple different ones. We'll pick one. We'll use iron metal, HCl, and then we need to neutralize. So we're adjusting the pH so that we isolate the free base of the amino group. So now we have 1,3-diaminobenzene. So we're at this stage, now we're going to make the diazonium. So we're going to use sodium nitrite, HCl, and again that generates nitrous acid, HONO, which will convert the amino groups to the diazoniums. So we end up with these diazonium salts. Typically you don't isolate these. You make them in situ, that means you make them and then use them. And then finally for our last step, we're going to treat with an excess of tetrafluoroboric acid with heat. So excess just because we need more than 2 equivalents of 1, 2. And that's going to do essentially substitute fluorine for the diazonium. So we have essentially 1, 2, 3, 4, 5 step synthesis to make 1,3-dichlorobenzene. Okay, so we'll go ahead and look at another example. So your book will use a lot of common names when referring to substituted benzenes. So for example, methoxybenzene is called Anisole. And so the next one we're going to look at is an Anisole derivative. So this is meta-chloro-anisole. So again, the meta means it's a 1-3 relationship. We see one of the substituents, chloro. The other substituent, like I said, is buried in that name, anisole, which is a common name. So anisole is methoxybenzene. So that's going to be like our parent. The chloro is at the 3 position. So we have metachloroanisole. Let's do a little summary, again, how we get these substituents onto the ring. And then in this part of the board, we're going to look at the strategy of how to sequence them. So chlorine. So how do we get chlorine? Chlorine is basically coming from just a substitution of the hydrogen with molecular chlorine and a Lewis acid. So iron trichloride. Alternatively, you can use aluminum trichloride. So that's a pretty straightforward substitution. So let me draw a dotted line. And again, what we're doing here is just how do we get that substituent itself onto the ring? And again, what we're going to do here is organize a sequence to properly get the right 1-3 relationship. So O-methyl. So we know how to get oxygen onto the ring, but it actually exists as an O-methyl ether. So we're going to need to use methyl iodide, sodium hydride to do an SN2 reaction. So that's going to convert the OH to OMe. So how do we get the OH onto the ring? That's going to come from treating the diazonium with copper oxide and water. So we can say at this stage we're going to OH. Then to get to the OH onto the ring, we need to start from the diazonium. And so we get to the diazonium from the amino with HONO. And so this is from reduction of the nitro, again, which we saw in the prior example. So iron metal, HCl, and then the amino itself is coming from the nitro. And so we know how to do nitration. So when we look at this, basically, this is sort of like the path backwards. So again, there's no carbons bonded directly to the ring, so we want to start with benzene instead of toluene. So we're going to start essentially with this part of the molecule first because of that being a meta-director. So we'll start with benzene. We're going to do nitration. And we can see that that group is eventually going to become this group through all of these transformations. And again, the reason why we want to start with nitration is because this is a meta-director. Again, it decreases the reactivity of the ring, hence the red arrow. It's showing the directionality of how it's putting in the second substituent, we do need it 1,3. If we started with chlorine first, chlorine's an ortho-para director, so we don't want to install that onto the ring first. So next we're going to install the chlorine, because that's going to get us the relationship right off the bat. So molecular chlorine and the Lewis acid aluminum trichloride. So there we are. We have the desired 1,3 relationship. The rest of the reactions now are just functional group transformations of that NO2 group into the O-methoxy using this identified reaction conditions already. So we'll go ahead and reduce that to the amine. So for example, we can use tin dichloride in ethanol. So we're getting the amino group, NH2Cl. So the chlorine is going to remain unchanged through the rest of this sequence. Now the diazonium with nitrous acid, HONO. So N2 plus, Cl minus. So we're going to displace. So when these reactions happen with these diazoniums, essentially you're losing nitrogen gas. So we're going to use copper oxide and water. So this oxygen is the source that gets onto the ring. So we're left with the phenol. So hydroxybenzene is a phenol. We have to do one more step, and that's install the methyl group. We can treat with sodium hydride. This is a base in THF, that's the solvent. And then the electrophile methyl iodide to do a Williamson ether synthesis. And so we have a 1, 2, 3, 4, 5, 6-step synthesis of metachloroanisole. So I think a good strategy when approaching these type of problems is look at the substitution pattern, and then for each individual substituent, look how you get it onto the ring. Then what you can do with that information is sequence it in the proper order so that you get, your desired 1, 3, or whatever the problem is asking you to do. So let's go ahead and start another one. So this will be para-nitrobenzoic acid. So let's convert the name into a structure. So para is the 1,4 relationship, benzoic acid. The following, there's the nitro group. So the thing about this one, the challenge as it were, both of these substituents that are on the ring are both electron withdrawing groups. So they're both meta-directors. So how do we get around that? Well, let me highlight this carbon right here. The carbon directly bonded to the ring, that's the benzylic carbon. So that's our indication that we want to start with toluene. So we have that carbon in place. So again, this is a common name, toluene. Methylbenzene. So this right away helps us by using that observation, because alkyl groups themselves are orthopara directors. We know that we can retain that carbon. So if we're assuming that the para is the major isomer that's formed, the first thing we can do is a nitration. So there's your conditions. Again, when you're taking your exam in Wiley Plus, you're going to want to be pretty well versed in knowing that, okay, these conditions are going to install a nitro group. So now look where we've come. We have the nitro group in the correct 1, 2, 3, 4 relationship. Now all we're doing is a functional group transformation of this to the acid. In the conditions that we've seen for that, use potassium permanganate, KMNO4, sodium hydroxide, water to solubilize everything, and heat. So once the reaction progresses and it finishes, then we're going to adjust the pH with acid so that we can actually isolate the acid and not the carboxylate. So there we have para-nitrobenzoic acid. So just as a quick review, this compound would have, if we count the carbons, the unique number of carbons, there's a mirror plane of symmetry. So we have 1, 2, 3, 4, 5 unique carbons. Notice all the carbons are sp2 hybridized, so they're going to occur at shifts. These shifts will be, say, 120 to 140. This shift, because it has a carbonyl, is, say, 180 to 220. So unique number of H's, we have 1, 2, 3. So with the para substitution, what that's going to look like in the aromatic region is basically this symmetric set of doublets. So this set, which integrates to 2, is split by these. So you do the n+1 rule. That's how you get a set of doublet and a set of doublet. And so this will be a singlet, a broad singlet by itself due to hydrogen bonding. So let's go ahead and take a look at a molecule that has 3 substituents on it. So again, the same strategy. We're going to look at how to get each individual substituent onto the ring. And then the challenge or the logic comes in putting those reactions in a sequence. So this one will be 4 nitro, excuse me, it's 4 iodo, 3 nitro, benzoic acid. So we want to convert this name into the structure, with the benzoic acid being the parent. The acid functional group is at carbon 1 of the ring. So if we're putting these substituents on, we have 3 nitro, we have 4 iodo. So again, when we're looking at this, our prompt is we're either starting with benzene or we're starting with toluene. We have this benzoic carbon, so it makes sense to start with a molecule that has it in place, and again, that's toluene. Alkyl groups are ortho-para-directors, and again, the green marker means that they react faster than benzene itself. So when we're looking at starting with toluene, we're basically looking to get in functionality at the 4 position first. Then we're going to have to do some stuff to direct over to this position at 3, and then ultimately do a functional group transformation of methyl into the acid. So we already saw how to get this to the acid in the prior example. So we know how to get nitro groups onto the ring with nitration, so that's straightforward. What about this iodine? So again, iodine is one of the halogens where we can't use just I2 in a Lewis acid. We're going to have to go back from iodine to the diazonium. The diazonium again comes from the amino group. And again, the amino group comes from reduction of the nitro group. So if you look, the iodine has to be installed through a nitration. So we can do that right away and get the nitro in the right spot. So let's do that, and then I'll come back to what would happen if we have both nitro groups on there at the same time. So nitric acid, sulfuric acid. So you have 2 substituents on there. The nitro group has to be transformed into the iodide using this series of reactions. But we need to get this other nitro group in there. So what do we need to do in terms of order? Well, if you look at how these existing substituents direct, the nitro group is a meta-director. We said the methyl group is an ortho-para director, para is blocked, so it's reinforcing where the meta group is directing, so that's no good. So what does that mean? We have to do a functional group transformation here. We have to reduce it. So let's go ahead for these reduction conditions. Let's use hydrogen gas, palladium on carbon in the solvent of ethanol. So hydrogen gas will do the reduction to the amine. So now this is an interesting example. We have basically paramethyl aniline. So aminobenzene is called aniline. We have a methyl group, so it's paramethyl aniline. So the reason this is interesting is because both of these substituents are ortho-para directors. The para positions are blocked, so they're each directing to their respective ortho. So I'm going to use a longer arrow for the amino group because the resonance will win out over induction. There's no lone pair here, so this is just donating through the bond. That's a weaker contribution to the ring. The lone pair going into the ring is much stronger. So the amino group is going to win out in the direction. So now what we can do is put in this nitro group. Nitric acid, sulfuric acid. So now where we're at is we have the right relationship we need. So look at what we're trying to achieve here. We have this 1, 3, 4 relationship. 1, 3, 4. So really at this point, the nitro group can stay the same. We don't have to do anything to it. It remains unchanged. We have to oxidize this. We have to transform that into iodide. So what we can do from here on in, the nitrogens are differentiated. So we'll treat with nitrous acid. And again, that's going to make the diazonium. Typically, like I said before, once you make the diazoniums, you make them and use them in situ. That means like right away in the pot. We'll dump in potassium iodide. That will do the substitution. Nitrogen gas will evolve. So we're almost there. We have the iodine and the nitro group. We're going to finish off with the oxidation of the methyl. So those are conditions to oxidize the benzylic carbon to the acid. And we end up with the desired compound. Nitrobenzoic acid. So 1, 2, 3, 4, 5, 6 steps. Again, so the first thing you want to do is be comfortable with how you get the substituents onto the ring. Next is functional group transformation. So example here, we're doing a reduction of nitro to amino. And then sequencing them in the strategy so that you get the right relationship. So here we have 1, 3, 4 tri-substituted. So let's go ahead and we'll look at another example. So the next one will have a Friedel-Crafts acylation in it, so we can see that chemistry. So how about meta propyl? So that's an alkyl chain. Phenol. So again, this is a 1,3 relationship between a propyl group, and again the other substituent is buried in there, hydroxybenzene, otherwise known as phenol. So there's phenol. At the 3 position we have a propyl group. So what is the challenge with this molecule? Basically, hydroxybenzene, this is an orthopara director, right? Let's write that in as a note. Alkyl groups are orthopara directors. So the challenge here is recognizing that you're going to have to install a substituent first that's going to direct meta. Then do a functional group transformation, basically to get these things into the forms they reside in the final product here. So what's a way to do this? Maybe as I'm thinking about it, another challenge with this propyl group is that it's linear, right? So to get a linear substituent on, you have to do a Friedel-Crafts acylation and then a reduction. You can't start with the primary alkyl chloride because it will rearrange and you'll get branching. So for this, we're going to have to start with benzene. And we have a choice. We know that OH groups come in through diazoniums, which come from amine groups, which come from nitro. We don't really want to start with a nitration because that really deactivates the ring, like too much, because we're going to have to do a Friedel-Crafts acylation. And a deactivated ring is not good for an acylation. So we'll start with benzene, we'll do the acylation first. We have 1, 2, 3 carbons. We're going to start with that acid chloride, so propanoyl chloride, we need to use a Lewis acid. And again, this generates a psyllium ion, which is the electrophile for a Friedel-Crafts acylation. So that's what we're doing here. So as a review, we start at oxidation state 3. We end up at 2 and we're making a ketone. The carbonyl is an electron withdrawing group. So it deactivates and directs meta. That's exactly what we want. So at this point, now we can do the nitration. So this ring is not so deactivated that this next reaction will not occur. But if you flip them, the nitrobenzene just is not reactive enough. So that's why we're pursuing this order of things. So here we go. We have our desired meta relationship, right? 1, 3. So what do we need to do now? This is at oxidation state 2. We need to reduce it to 1. So that would be a Clemmensen reduction. This we need to transform into the OH. So that would be reduction to the amino, diazotization, and then treatment of the diazonium salt with copper oxide. So let's go ahead. We'll reduce this with zinc, mercury amalgam, and HCl. So these conditions for reducing a side chain, that's known as the Clemmensen reduction. So we reduced that from 2 to 0. We have our nitro group. Let's use tin, dichloride, and ethanol. That's reducing that to the amine. Nitrous acid transforms this into this diazonium. And then finally, we're going to treat the diazonium with copper oxide and water. And again, the oxygen is coming from the copper oxide to install the hydroxy substituent. So here we have metapropylphenol. And again, the challenge here is that if we look at the compound we need to make, both of these are orthopara directors. So we basically have to do a Friedel-Crafts acylation to install the ketone, which is going to direct meta. So we have 1, 2, 3, 4, 5, 6 steps, starting from benzene to end up with this desired product. So let's go ahead and look at one more. Four cyano benzaldehyde. So benzaldehyde, again, is a common name. So there's benzaldehyde. The 4 position, we have the cyano group. We know that we can install a cyano group basically from a diazonium. Using copper cyanide. And again, this comes from the amino group, which comes from the nitro group. So we're starting with a 1-4 relationship. We're going to use this sequence of reactions to get that substituent in. We have a benzylic carbon that's oxidized to oxidation state 2. So basically it's going to be more straightforward for us to start with that carbon already on the ring. So in terms of that, we can start with toluene. So one way to move forward with this we know that again, the alkyl groups are orthopara-directors. So if we immediately take advantage of that, we can get the 4 position substituent in there in terms of a nitration. So that's going to get us that desired relationship. So what you can see now is just a series of functional group transformations. So I would say, just to explore some other chemistry we haven't seen so far, we have a benzylic methyl group. We can do benzylic substitution. So if we treat with NBS, as a reminder, NBS is N-bromosuccinimide. And light, that's going to do a radical halogenation at this position. It's not going to react with the ring. So there's where you want to be clear about reagents and what functional groups they act upon. So now we have this benzylic bromide. And essentially what we want to do is get the oxygen in there at this point. So we are going to do an SN2 reaction. We're going to displace that bromine. We're going to use sodium acetate to get the oxygen in. So acetate is that acyl portion. So we have the oxygen in, we just need to do our diazotization chemistry and then an oxidation at the benzylic position. So what if we did the following? If we reduce this down to the amino group with iron, HCl, heat, and then we adjust the pH with sodium hydroxide, that's going to accomplish 2 things. It's going to reduce this to the amino group, and then these conditions are also going to saponify that ester. So we saw that in module 2, saponification reaction. And essentially what it does is free up the alcohol. So we're at this position now. We can go ahead and treat with, I'm going to condense this sort of into 2 things here. Nitrous acid transforms that into the diazonium. Then we can treat that with copper cyanide to do that displacement of the diazonium to get our cyanide at the 4 position. And so we're in oxidation state 1. We need to be at oxidation state 2. We can use pyridinium chlorochromate. Remember that from module 1 this semester. So we oxidize to our aldehyde. So in 1, 2, 3, 4, 5, 6, 7 steps, starting from toluene, we were able to make 4-cyanobenzaldehyde. So let's, we'll go ahead and wrap up this sort of mini lecture. And basically, we've looked at a couple different molecules, converting the name into a structure, applying known reactions in a sequence to end up with the desired relationship between the substituents.